So we've been talking about integrals, and the integral is basically the sum of many parts. It can be the area under a curve, and what we're going to look at now is finding the volume of a cone by using an integral. So if you have a cone, there are many different ways you can slice it. One way to slice it, for example, would be to come up with this little pie wedge and then rotate that wedge around. So instead we're going to look at a pancake, basically. And we know that the shape of this is a circle, and the area of a circle is going to be pi times the radius squared. In order to find the volume, I'm going to have to tell you the total radius at the base of my cone. I know down here r equals 0 because it comes to a point, and the height we'll call large h. Now this pancake is a circular shape, but it also has a thickness. And in general, volume is going to be the area times the height. And so my height this time is going to be dh. So if I want to sum these up, I will have the integral of pi r squared dh. And this is what I'm going to try to solve. You notice this is dh and this is r. So what I need to do next is write r in terms of h. Now the cone can be drawn as a triangle if we just draw the line down the middle of it. So here we have r and h, and this is an angle theta. And we know that the tangent is the opposite over the adjacent, so that would be r over h. Tan theta equals r over h. Well, if I consider a smaller triangle right here, consider that I was part of the way down the cone, this would be little r, and this I can call little h. So the tangent of theta is also little r over little h. I can solve for r, and I will get r equals big R times h over big H. And I take this and plug it in right here. So now we have an expression for r in terms of little h, and we need to substitute this in, and then we can take our integral in terms of h. So we'll have the integral of pi times r times little h over big H squared times dh. Now up to this point we have not talked about our limits of integration, but we need to consider the smallest and the largest values of h. So if we come back to our cone, at the bottom h equals 0, and at the top, what's the value of h? Well, it's our total height, so h equals capital H. So as we're doing this integral, we're going to integrate from h equals 0 to capital H. So now I'm going to square this and then take my integral. The integral from 0 to capital H of pi times big R squared, little h squared, over big H squared, dh. I can take my constants to the front, so I'll have pi r squared over h squared times the integral from 0 to h of h squared dh. Carry my constants forward, r squared over h squared. The integral of h squared is h cubed over 3. I will evaluate that at 0 and at h. This gives me pi r squared over h squared times big H cubed over 3 minus 0 cubed over 3. Don't forget the lower limit. In this case it does cancel. H cubed over h squared. It's going to leave me with h. So my final answer is 1/3 times pi r squared times h, which is the volume of a cone.
To review, we started the problem by making a diagram and determining how to best slice the volume to set up the integral. The general formula for a volume is the area times the height, The formula for area in this case was that for a circle. We returned to the diagram to solve for r in terms of h. We made the substitution and determined the limits of the integration. And finally, we integrated to find the volume of the cone. If you were to look up the formula for the volume of a cone in terms of r and h, you would find this equation. The second example is a cylindrical integral. Suppose you had a cylindrically symmetric vase with the cross-section shown here. When rotated about the x-axis, the shape would look like this. In order to solve for the volume, follow the same procedure as for the Dixie cup. The difference is that rather than finding circles of varying radii and integrating along the height, we will rotate the cross-section around the axis. This requires the volume integral shown here. Notice it is based on the same expression we used earlier, pi r squared h. In this case, we substitute f of x for r, much like we solved for r in terms of h in the previous example. Continue through the math, and the answer reduces to 9 pi squared.